Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on July 31st, 2025, so just about 5 days ago. This paper offers a really clear explanation for a long-standing question. Why does classic Softmax attention, which is the mechanism that lets models like GPT-4 focus on relevant words, consistently outperform more efficient linear attention methods? The paper is titled, On the Expressiveness of Softmax Attention, a Recurrent Neural Network Perspective, and as we'll see, the answer has to do with seeing attention in a whole new way. They find that Softmax attention's power comes from its ability to model an infinite series of interactions, and that linear attention is really just a simple first-order approximation of this process. And it looks like this new perspective is getting a lot of attention online. Researchers and enthusiasts on X are highlighting how the study explains Softmax attention's power by revealing it's essentially a recurrent neural network in disguise. One post with over 160 likes points out how this work finally clarifies the performance gap between the classic, computationally expensive method and its faster approximations. Others are calling it a great plain English lowdown on why modern AI models are so good at paying attention. Alright, so this diagram here really lays out their core idea. It breaks down Softmax attention into a series of parallel processes. The section on the left, highlighted in red, is what we typically call linear attention, but it's just the first step. The full Softmax mechanism is actually an infinite sum of this linear part, plus a second, a third, and so on. These additional parts use a mathematical operation called a Kronecker product, which allows the model to capture much more complex, higher-order interactions between its inputs. Okay, so to test this new recurrent view, the authors focused on the denominator in the original Softmax equation. They tried replacing it with two things: a gate to control information flow, or a simple norm to stabilize the math. These charts show the model's error, or loss, during training on large datasets, and the results are striking. The purple line, representing the norm version, performs identically to standard Softmax. The gate version, that yellow line, performs slightly worse and was reportedly less stable during training. So the next logical question is, does this hold up when you scale things? These charts show exactly that. The authors tested this in two ways: by using a much larger model, around 2 billion parameters, and by using much longer input sequences. And the results are consistent. The top and bottom graphs show that the norm-based approach, that purple line, scales identically to standard Softmax. The gate version still performs worse, and you can see it was unstable during training, with that big loss spike in the top right chart. Building on that, the authors then test what happens when you add these higher-order interaction terms back into the models. The top left chart shows that for their recurrent Softmax approximation, adding more terms smoothly closes the performance gap, until it's nearly identical to the real thing. But for the linear attention variance in the other charts, it's a different story. For cosine attention on the top right, adding more terms does almost nothing. And while the other variants improve, they never fully catch up, showing a fundamental performance gap. So in the end, this work offers a really elegant explanation for why Softmax attention remains king. Its power lies in those infinite higher-order interactions, and its denominator is really just there for stabilization, not for its specific mathematical form. That's it for this episode.